Okay, this is a video on relative motion. All motion is relative to some frame of reference. The most common frame of reference for us is the Earth. We think right now that we're sitting still. In actuality, we're traveling very, very fast. The Earth is rotating around on its axes. It's revolving around the sun. The sun is actually revolving around the center of the galaxy. The galaxy is actually hurtling through space. So we have a lot of very complex motions, but because we gauge our motion relative to the Earth and to the ground, we say we're sitting still because the ground appears to be in the same position we are. So the first thing you have to realize is that all motion is relative to something. Okay. The next thing is we have this very silly formula. It goes like this. Okay, the velocity of an object, A, relative to C, is equal to the velocity of object A relative to B, plus the velocity of object B relative to C. That formula looks like gobbledygook and makes no sense until you start putting it into play with an actual example. So consider an arrow. We have an arrow going through the air, and let's say it's traveling at a speed of 20 meters per second relative to the air. So you fire the arrow, and if you're measuring it relative to the air, it would be going 20 meters per second. So that 20 meters per second is the velocity of the arrow relative to the air. But the air is also moving. Let's say the air has a wind blowing through it, and the wind is blowing in the same direction that the arrow is moving, and it's blowing at, say, 10 meters per second. And we measure that airspeed relative to the ground. So we would say the airspeed has a velocity. So we have the velocity of the arrow to the air, and we have the velocity of the air to the ground. If we want to know how fast the arrow was going compared to the ground instead of the air, well, we'd take the 20 meters per second plus the 10 meters per second. And that would give us the speed relative to the ground. And that, of course, would be 30 meters per second. So 20 plus 10 is fairly easy math to get us to 30. This equation up here looks kind of bizarre. But again, once you put it into an example, it looks much easier. Let's try a different example. In this second example, we still have the same arrow. It's still going 20 meters per second to the right. But now the wind is blowing the opposite direction. The wind is going against the arrow to the left, and so we'd call that a negative 10 meters per second. So the velocity of the arrow to the air, so arrow to air, is 20 meters per second. The velocity of the air to ground is a negative 10 meters per second. So the velocity of the arrow to the ground is equal to the first velocity plus 20 meters per second plus the second velocity, which is a negative 10 meters per second. In other words, we would have 10 meters per second to the right. Consider the example of the gentleman running on the railroad cart. Okay? If the railroad cart is going 8 meters per second to the right, and he's going 4 meters per second relative to the cart to the left, then his velocity relative to the ground would be the negative 4 meters per second, because we call going to the left negative, plus a positive 8 meters per second. So in drawing A, his speed is relative to the ground a positive 4 meters per second. Let's look at situation B. This is an active guy. Here he's going 6 meters per second to the right relative to the railroad car. So we have a positive 6 meters per second. The railroad car is going to the left at 10 meters per second, so it's a negative 10 meters per second. So the gentleman's speed relative to the ground, so his speed relative to the ground, is equal to 6 minus 10, or a negative 4 meters per second. Consider situation C. The gentleman's speed relative to the railroad car is a positive 4 meters per second. The railroad car's speed relative to the ground is a positive 6 meters per second. So the speed of the gentleman relative to the ground is 4 meters per second plus 6 meters per second, or a positive 10 meters per second. Finally, let's do case D. The gentleman's speed relative to the railroad car is a negative 6 meters per second. The railroad car's speed relative to the ground is a positive 18 meters per second. So the gentleman's speed relative to the ground is equal to a positive 12 meters per second. Starting to get the idea now? Let's take a look at a diagram from the Minds on Physics website. We have a plane right here, and it's going at a velocity of 100 kilometers per hour. There's also a wind blowing on that plane, and we call that a tailwind. It's going in the same direction as a plane. That's what a tailwind does. It blows at the tail. So the plane relative to the air is 100 kilometers per hour. The air relative to the ground is 25 kilometers per hour. As a result, the plane relative to the ground, plane to ground, has a speed of 125 kilometers per hour. One more example, we have that same plane and it's still going at 100 kilometers per hour. And the wind is still blowing, but now the wind is blowing in the opposite direction. We call that a headwind because it's blowing at the head of the plane. So it would be a negative 25 miles per hour. So plane to air is 100 kilometers per hour. Air to ground is negative 25 kilometers per hour. And the resultant velocity of the airplane, plane to ground, is 75 kilometers per hour. And that's a very real effect. This relative velocity is really important in planes. That's why it's much faster to go from California to Chicago, because you've got a tailwind most of the way, than it is to go from Chicago to California, because you have a headwind most of the direction. And that's all on relative velocity. Thank you very much.